Hi, Geometry. This is probably the last video of the year, so you can celebrate. And um, you're probably going to miss these videos over the summer. Let me know. I'll hook you up with the pre-calc. I don't have videos for Algebra 2. Sorry about that. All right, here we go. This is probably the most complicated section, but hopefully I can simplify it enough for you and just give you a taste of what's going to be in the future. Especially, this is a big topic for AP statistics. And you'll get a little bit of this in Algebra 2, but just a tiny bit. So here we go. Finding probabilities of independent and dependent events. And the key word here is and. Remember how the last section we were doing or probabilities, we were adding them. Now we're doing and probabilities where you're going to multiply them. So I will examine independent and dependent events, and I can find the probability of an event. Okay. So here we go. Two six-sided dice are rolled. Okay, so what do you do if you don't have that picture with all the dice on it? Well, how can we get a sum of 7? Our choices would be like a 1, then a 6, 2, 5, 3, 4, 4, 3, 5, 2, and then 6, 1. So 1, 2, 3, 4, 5, 6. So that probability is 6 out of 36. You should know that there are 36 events there, which is 1, 6. How about the probability of 5 or 7? So I've got the sum of 7. So probability of 5 would be 1, 4, 2, 3, 3, 2, and 4, 1. There's 4 of those. So this will equal 4 out of 36. Or we can get the sum of 7, which would be 6 out of 36. That's equal to 10 out of 36. And they were mutually exclusive. You can get one or the other. There's nothing in common for those. So that's why we don't subtract anything. When you reduce this, you get 5 out of 18. All right. How about this one? You toss a coin 3 times. What's the probability of getting heads? All right, so I'm going to have to write really small here. I'm going to do a tree diagram because I want to keep introducing that to you because I want you to see that they can be handy. So first, heads or tails. That's my first toss, okay? Then from there I can go heads, tails, heads, tails. So this is my second toss. And then heads, tails, heads, tails, heads, tails, and last but not least, heads, tails. So what's the probability of getting 3 heads? Well, the only way we can get 3 heads is right here. So that's 1 out of 1, 2, 3, 4, 5, 6, 7, 8. 1/8. Now what if I asked you, what's the probability of getting at least 1 tail? Okay, so this would be heads, heads, heads. There's no tails there. Here's 1 tail. Actually, if I list these, heads, heads, heads. This one would be heads, heads, tail. This would be heads, tails, heads. Heads, tail, tail. Tail, heads, heads. Woo. Tail, heads, tail. Tail, tail, heads, and then tail, tail, tail. Now, wouldn't you agree this is the only one where you don't get at least 1 tail? So this probability is going to be 7/8. It would have been a lot easier to do 1 minus its complement, which is 1 minus the probability of no tails. So 1 minus 1/8. So the complement. Remember, I told you complements will pop up a lot. So, okay, here we go. 2 events are independent if events of the occurrence, wow, my typos, of one event does not affect the other. So they're independent. 2 events are dependent. Okay, so I wish I would have bolded those. If the occurrence of one event does affect the occurrence of the other. Okay, so here's independent. If I want the probability of A and B, you're just going to multiply them. But what if event A makes a change of this? So then they'd be dependent. So the outcome of the events affects the outcome of the other. So if A and B are dependent events, the probability would be You have the probability A, so these are the same, but this means the probability of B given A has happened. I know that sounds kind of weird, but I'll explain that in a second. So the probability that event B occurs given that event A has occurred is called the conditional probability of B given A, and it's written like this. This is the conditional probability of B given A. Note that A and B are independent events if and only if these two equal the same. Okay, this is actually really important. Your book doesn't touch upon it that much. So think about it. This is the requirement for independent, and this is for dependent. Well, the probabilities of A's are the same. So if these two are the same, then it's independent. Okay. Since the probability of B does not depend on the occurrence of A. So, probability of A and B is equal to this or that. So it's kind of like your key equation. Now, how does this work? I know that was confusing, but it'll make more sense when you actually do problems. A card is randomly selected from a standard deck of 52 cards. Find the probability of the following, or find the following probabilities. You want the probability of a 6 and then a king. So you're taking out 2 cards, but you're not replacing one. So the probability of let's just look at the probability of a 6. You have 4 out of 52. And the probability of getting a king is also 4 out of 52. So what's the probability of doing one and then the next one? So you're going to have 4 out of 52. But once you take that 6 out of the card, or the deck of cards, how many cards are left? 51. So the probability of getting a king, given a 6 was pulled out, you have 4 out of 51. So this is a dependent event because the probability of a king was changed, because that was without replacement. But what happens with replacement? Meaning that means you put the card back. So what's the probability of getting a 6? 4 out of 52. And then the probability of king, and you put that 6 back in the deck. So you now have 52 cards back in the deck. And you get your answers. 6 out of, let's see here, this will be 16 out of 26, 52. Who knows what that reduces to? This will be 16 out of 2704. This one is independent. Okay? So that's the difference between the two. All right, let me show you how these can change. Now, spinners are notoriously independent problems. Of course, I ask you that right here, but look at there. So we have 1, 2, 3, 4, 5, 6, 7, 8. There's 8 equal parts. Find the probability that you get a red on the first one, and then a blue. So that's going to equal the probability of the red and then the probability of the blue. So I can spin red all day. It's not going to affect my next spin. So these are independent. So the probability of red, let's see here. We have 1, 2, 3 reds. And then the probability of blue, we have 1, 2, 3, 4. 12 out of 64. And that reduces to 3 out of 16. So if we divide the top and bottom, this is definitely independent. So spinning is usually independent. Okay. How about this one? A bowl contains 54 hard candies, and then 36 chocolate. We have a total of 90 candies in a bowl. You know, there are some freaks that will count. You randomly choose a piece of candy, you eat it, and then randomly choose another piece. So what's the probability of getting chocolate and then a hard candy? So probability of chocolate would be 36 out of 90. And then we got a piece of hard candy. So we have, 54. But now there are only 89 pieces in there. So this is, here this is the probability of A times the probability of B given A has happened. Okay, so this is dependent. And I really don't know what those numbers are. Go ahead and multiply across the top and bottom. You'll figure it out. How about this one? Probability of a chocolate and another chocolate. So chocolate would be 36 out of 90. Well, now we have 35 chocolates left out of 89. Oop, let's multiply those. And again, this would also be the same idea. Okay, so given a chocolate piece was already taken. Are these independent or dependent? These are definitely dependent. Okay. So conditional probability. We had this equation, probability of A and B is equal to probability of A times the probability of B given A. Well, what if I want to get this by itself? Divide both sides by the probability A, and then these cancel, and this is what you'll have. Okay? So, because sometimes you might need this to solve a problem. You may or may not. All right, now, how do independent and dependent events work with a two-way table? All right, so here we go. Number of times a student visits tutoring, so 1 or fewer times, 2 or 3 times, and then 4 or more. Okay, so this is 2 to 3, this is 1 or less, so 1 or none. You have full-time students and part-time students. Now what's interesting is, notice they added these across and got 45, 13, 58. So there's a total of 58 students. Lots of times they will not give you these totals, and I think I gave you a two-way table where you did not have a total. So let's go ahead and, if a randomly selected a student is randomly selected, what's the probability they are a full-time student? Well, how many full-time students do I have? 45 out of 58. This does reduce. But now reducing these fractions can get a little tricky, so you can go ahead and write down those decimals. AP always wants 3 decimals, so I say if you go 4, it's never going to hurt you. I might put 3 sometimes. Okay, now look at this. I have the word given in here. The person's going to visit 5 times given full-time student. That means I'm only going to deal with full-time students. Well, how many full-time students do I have? 45. So that's going to be your bottom number. So they're going to visit 5 times. That would be in this column. So you have 8 out of the 45. So as soon as you have given, that's going to be your bottom number. Okay, so it's not going to be out of 58. That's about 0.178. Okay, so they visit one time or more than 4 times. Okay, so this is mutually exclusive. So how many visit 1 or fewer? We have 14 out of 58. Notice how I'm mixing up the sections now. Or means add. And then 4 more times. That's also 14 out of 58. So you have 28 out of 58. And that's what? 14 out of 29, which is about 0.483. So almost 50%. And then, how about you have a part-time student and they visit 2 times. Okay, so now we're not multiplying here. This is like one person. They're a part-time student and they visit. So here are my part-time student things, and visiting 2 times are right here. What do they have in common? So this is what they have in common. There's 5 of these out of 58. So this one's kind of tricky, and that reduces to about 0.086. Okay, here's a good one. These came from a guy named Stu Schwartz. Master Math Mentor.com. Basically, your whole AP community uses these problems. So I'm going to read this, and you're going to panic, but we're going to use a tree diagram to figure it out. So that's what I have the space up here for, is the tree diagram. So it is estimated that 4% of the people who spend time in the woods will get Lyme disease. So that means 96% will not. So let's see here. I'm going to separate it like this. Those who get Lyme, that's 4%, 0.04. And then not. That will be 0.96. Okay? The test to determine if you have will give a positive reading 97% of the time. So if you have Lyme disease, it'll test positive. 97%. But that means if you have Lyme disease, 3% will say negative. That's scary. Can't figure out why you're sick. Okay. Of the people who do not have Lyme disease, that's down here, the same test will give a negative rating of 92%. So if we don't have it, that's 92%. But that means 8% are tested positive. Okay, so what percentage of people with Lyme disease test positive? So what you do is they have this and that. So we got to multiply these. 0.0388. I did the math ahead of time. How about those who have Lyme disease but test negative? This is really scary. I know 4 times 3 is 12, but then I have 4 behind the decimal, so 0.0012. How about you don't have Lyme disease and you test positive? That's kind of shameful because you're taking all this medication and you have something else maybe. Multiply these, 0.0768. And then you don't have Lyme disease and you test negative, so it's more comforting. You get 0.8832. What's going to happen if I add those up? The sum is equal to 1. It should make sense. Okay. Now, what's the probability that you get a positive reading? Well, there's 2 ways to get a positive reading. Right here and right here. So you have 0.0388 plus 0.0768. That's going to equal 0.1156. So that's the probability of a positive reading. How about the probability of a negative reading? It's these two. 0.0012, because there's 2 ways to get a negative reading, plus 0.8832. When you add those up, you're going to get 0.8844. So that's the probability of a negative reading. So now this is how C and D are going to come into play. So if a person has a positive reading, so this is like my given. Notice how up here I wrote given this is happening. So given this is happening, they have a positive reading. Okay, so if you have a positive reading, that is your bottom number. That they have Lyme disease. Okay, so that's the 0.0388. I know this is tricky. You're going to definitely see this in high school, but probably not to the senior year. When you divide them, you're going to get 0.3356. Okay, so given you have a positive reading, so that's the same bottom number. You don't have Lyme disease, so the 0.0768. And you'll get 0.6644. Okay, given we have a negative reading, so now we're going to use our negative reading stuff. This will be my new bottom number, 0.8844. That you don't have Lyme disease. So 0.8832, we do not have it, 0.8832. And you'll get 0.9986, so that's most likely to happen. You get a negative reading given you don't have it. Alright, so bottom number is 0.8844, that you have Lyme disease, and that'd be the that you have it, but it's negative 0.0012. 0.0014. So that's how you do those problems. This is definitely extra, but I want you to realize how stats can be expanded. You'll not be tested on this, but I would love to give it to you as extra credit on a test if possible. All right, so here is our homework assignment, the last homework assignment of the year. I always say that, but if we have more time, we'll do other stuff. Here are all of our standards, and you have a very nice, happy spring break and happy Easter.